This video will be a tutorial on how to design a NAR or Tripoli certified level 1 rocket using the program OpenRocket. The design I'm going to show you has been tested by me, and I flew it for my level 1 design, so I know that it does work. It should also work for a level 2 rocket certification, which is another reason that I like this design. So OpenRocket, which I have set up right here, is a free to download program that's super useful for making level 1 and level 2 and even some level 3 designs. In order to have OpenRocket running, you do need to have Java also up and running on your computer. I will have links in the description below to OpenRocket and Java downloads. So when you first open up OpenRocket to make a new design, you can either start with a nose cone, a body tube, or a transition piece. So I'm going to start with a nose cone. So when I click on nose cone, it generates this just automatic design that the computer just has saved in it. And this dialog box comes up, and this is where you can input all of your different dimensions, and it's a very similar box for all the other parts as well. So for the nose cone, you have to, and this applies to all the parts really, you have to make sure you're putting in dimensions of parts that you can either buy online or you can manufacture yourself. So for most of the parts I'm going to be showing you, I bought them online, and then when I got them, you epoxy them together and all that stuff, except for the fins. The fins, generally, I make those from scratch because they're usually shaped in a way that, you have to make them on your own. So I'm going to start with the length here. The length for the nose cone I found online, and I'll have links in the bottom to these websites that I found these parts from. The length I found was 13 inches. So you can see now it's changed in this window right here. And the base diameter was 3.1 inches. And this box right here, you can, I'm not going to check that for right now. It's just another option. If you go over here to shoulder, this is where you're going to insert the dimensions for the part of the nose cone that sticks out into the body tube. So generally a good rule of thumb for these sorts of things, and it doesn't just apply for the nose cone, it also applies for body tube couplers and all that kind of stuff, is that you want your shoulders to be as long as the body tube is wide in diameter. So for example, my body tube diameter for this design is 3 inches, so I'm going to make my length, and you'll see that when you find these parts, they will tell you these dimensions, but it's just a good thing to know why it's 3 inches. It's just a rule of thumb. So I'm going to make my length 3 inches, and the diameter is 2.99 inches. It's not exactly 3 because you see there's a little gap right here. It has to fit inside the body, and then the nose cone rests on the body tube here later. You'll see that when we add the body tube. And I'm going to check this box for end capped. And what that means is that it's actually cut, or it's closed off right here. Some nose cones are actually open, so you can go inside, but generally speaking, for a 3-inch diameter nose cone, they're not going to be. If you have a 4-inch or a 6-inch diameter, it might be open there. The thickness, this really just concerns the weight of the nose cone, basically. So I'm just going to put that as 0.1, and then this one is automatic. It automatically gives you a wall thickness. But I have measured the weight of this nose cone, and sometimes you'll see on the manufacturer's websites that you're buying the parts from, they'll give some kind of a mass to whatever their part is. If not, you'll just have to leave it as the automatic, and it does calculate a mass for each part. You can see it at the bottom of the dialog box, component mass 3.84 ounces. But generally, to make your models more accurate, when you actually get the parts, you should always weigh them on a scale, and then you go over to this override tab here and click on this box right here for override mass. that will then allow you to enter some mass. So the mass I had for the nose cone that I bought was 5.89 ounces. And by the way, you can change your units at any time by just clicking on the unit itself. It gives you this option. So one thing before you finish up with the nose cone, you have to make sure you're using the right material. So the material for my nose cone, I believe, was polycarbonate, which is just like basic plastic. Another really common material is, of course, fiberglass. If you're going, close to the speed of sound, you're probably going to want to use fiberglass with the metal tip. But this rocket won't be going that fast, so I'm just going to be using polycarbonate. So I'm going to close out of there now. And before I move on, there is one other thing I want to show you guys. If you go up here to edit and you go to preferences, this is where you can change your units and lots of other things. So right here is where you can change your default launch settings. We'll get into that more later or possibly in the next video, depending on how long this runs. But right here is what's important for this video, your units. So you can do default metric or default imperial. I believe the first time you open up OpenRocket, it's going to default to metric. But generally speaking, all the suppliers we're going to be buying from for body tube parts, nose cones, and things like that, they're all going to be measuring in imperial or US units. So you want to click this default imperial. That will change you to US units. And you see also this blue weight right here means that I've set a weight to it. So I'm not using the default mass as calculated by OpenRocket. I'm using a mass that I input manually. So the next part I want to add is a body tube. So I'm just going to click on body tube right here, and it's going to automatically add a body tube that already has the outer diameter of the base of the nose cone, so that they line up. And that's usually good. So you can leave this box checked as automatic for that. But the inner diameter is not quite exactly what I want to be. The inner diameter of the body tube that I found was actually 3 inches. So I'm going to input that right there. And for the material, I selected blue tube. So blue tube is a little bit stronger than cardboard, but not as strong as fiberglass. It's really good for a level 2 design. It gives you a happy medium between cardboard and fiberglass. It's much easier to work with than fiberglass is and less dangerous, so that's nice. And it's also a lot less expensive than fiberglass, but again, still stronger than cardboard. And it literally is a tube that is blue color, so that's how you know what it is. So I'm going to go over here to, actually first I got to change my length. So my body tube is going to be a lot longer than 7.8 inches. The length I have for my body tube is 48 inches. Oops. There we go. So now that automatically adjusts. So the mass that I found for my body tube also, let's see, was 19.8 ounces. Okay. So close out of there. And now we're starting to get something that looks a little bit more like a rocket, but there's still quite a few parts we have to add. So in order to add the parts from here, they're actually going to be parts that are dependent upon the body tube. Like, we obviously still have to add fins and centering rings in the motor and all that stuff, but they're grayed out. We can't click on them right now. So how do you do that? You need to come over here and you need to click on body tube. And once you click on the body tube, you'll see that all these other options are going to be available for you now. So for adding fins, which is the next step that I usually like to do, you have 3 options: trapezoidal, elliptical, or freeform. Elliptical and trapezoidal are pretty similar. Freeform is a little bit more of an advanced technique, so we're not going to get into that right now. So I'm going to go do trapezoidal because that's really all you need for level 1 or level 2 rocket. You don't need anything fancy. So this is probably the most complicated part of the design. The fins are always the most complicated part of the design. So I'm going to do 4 fins. And this first thing is where you can change the number of fins that you want. Fin rotation and fin cant, I'm just going to leave those as 0 for right now. What that would do is the fin rotation would basically rotate them around the body. So it's in degrees. Then the root chord is the measurement from this corner to this corner right here. So for me, that was 7 inches. And now you can see that changes. The height is measured from the outer diameter of the body tube here, where the fin connects to it, to the tip of the fin. So that for me is going to be 3 inches. And now the sweep length, it's a little bit difficult to show on here, but it is the linear distance between this point and this point. So it's not the distance of this line here, it is the distance in the x direction. So basically like from about here to right about here right now, but I'm going to make it a bit longer, and I'm going to go with 2 inches. And that's going to also automatically change the sweep angle. The sweep angle does basically the same function. And one thing I just forgot real quick is the tip chord here, which is the same as the root chord, but for the tip of the fin, it's the measurement from this distance, this corner to this corner. Mine was 4 inches. Okay, so one thing I want to say before moving on is one reason that I've chosen to do this type of design instead of something, say, like this, is because if you have this case, you have corners of these fins right here that could break off very easily upon landing, because generally speaking, when you land, the first part of your rocket to touch the ground is going to be the corner of a fin. If this is for a certification flight, then and your fin chips off or something like that, you will be disqualified. So it's a lot safer to have something like this, where you have a much more, you have an obtuse angle. The stress concentration is much lower in this corner if something were to hit it. And also you have the base of your rocket being the closest point to the ground if the rocket is falling down this way. So that's the first point that's going to hit. It's going to help to distribute the force a lot better than just a tiny little tip of a corner of a fin hitting the ground. So the thickness I made for my fins was 0.125 or 1/8 of an inch. Generally speaking, the thickness is going to depend on what type of material you're using and like what kind of strength you want to achieve out of your fins. So if you're going like supersonic or something, you might want to make them, more robust. I'm going with 1/8 inch, and I'm going to use fiberglass for my fins. If, even for a level 1 design, when you're not going too fast and you want to use plywood out for your fins, which is perfectly fine, I would suggest using 1/4 inch, because 1/8 inch plywood is really just going to snap as soon as it hits the ground. So if you're planning on using plywood, again, I would up this to 1/4 inch. Now, the fin cross-section right here, this is going to have a huge effect on the flight of your rocket as far as what altitude you're reaching and how fast you're going. So the optimal case right here is the airfoil. This is the most streamlined case. Your fins will, go through the air like a hot knife through butter. But that's really hard to achieve unless you're using really accurate CNC machining and you want to spend many, many hours making these fins. So in most cases, you're probably going to go with rounded. Square is the worst case design. Again, this is talking about the cross section of the fin. So basically, if you were to slice this rectangle this way and look down on it from the top, it would look like a very thin, long square. or it would look rounded or like an airfoil. I'm going to go with rounded for this design. And then another thing that's important about the fins is the tabs. So unless you plan on welding your fins directly to the body, which if they're made out of metal is fine, but I don't recommend that. That's probably much too complicated for a level 1 or level 2 design. If you're just doing fiberglass or wood, you're going to need tabs that will stick into the body of the rocket. You'll see what I mean here in a second as I enter these values. Right now there are no tabs, so it's a little bit confusing. I'm going to go ahead and enter these values and then explain them in just a minute. So for the tab length, I have 5.625 inches. And for the tab height, I have 0.732 inches. And for the tab position, I am doing it, and this is another thing that we haven't really come into contact yet with the body tube or the nose cone, but when you're entering positions for components, you're going to have options as to where to do it relative to. So for the fins, you can do it relative to the root cord leading edge, which is this corner right here, the root cord trailing edge, which is this corner in the back here, or the root cord midpoint, which is somewhere right around here. It's right in the middle of this corner and this corner. So I'm going to measure mine from the root cord trailing edge, and I'm going to measure it negative 0.375 inches. So the reason that I've put all of these very, very specific measurements in, it will be clear in a moment when we add the motor mount tube, but basically it has to do with the fact that you want your fin tabs to come right up to where the motor mount tube is. So you want them to be able to connect to the centering rings, which are going to be mounted here and here, as well as the motor mount tube, which is going to be here and here. If you're a little bit confused by that, don't worry. It will make sense in just a minute once I add the motor mount tube, and I'll zoom in so that you can see exactly how these things are coming together. One other thing I want to say about the fins is that the fins are probably the component that has the single largest effect on your stability, and they're also the most easily editable. So you can, change them super easily on here to tweak your stability in certain ways, which your stability is measured over here. We'll get into this more later once a motor is added and we're analyzing stuff. But the fins are a really easy and fast way if you want to just bump up your stability by, just a couple tenths of a caliber or something like that. The fins are probably the easiest and fastest way to do that. So the other thing, before I add a component, you now see that the trapezoidal fin set is a child component of the body tube. So again, you see everything's grayed out here. Once I select the body tube, now I can add more stuff, and it's going to go into this same design tree that the trapezoidal fin set is in. You could also add things based off of a trapezoidal fin set, or any of these components for that matter, or not the fin set, but other inner tubes can be done in that way. So the next thing I'm going to add is the motor mount tube. So I'm going to click on inner tube right here, and that's going to come up again as a child component of the body tube. And now you can see what I mean by child component. The position of the motor mount tube is measured as relative to the bottom of the parent component, which again is the main body tube. You can change that if you want, so you could do like middle, and I don't know, you could set this like 5 inches. Now it's like this red rectangle here is the default size made for the motor mount tube. It's measured 5 inches away from the middle of the body tube. But generally speaking, you want to leave it as bottom of parent component, and you want to set this to be 0 inches so that your motor mount tube, the bottom of it, lines right up with the bottom of your body tube right here. So the dimensions I found for the inner tube I want are 1.635 inches for the outer diameter, 1.525 inches for the inner diameter. The wall thickness is going to be calculated automatically based off of that. And then the length, I want that to be 20 inches. So you may find that, and this applies for body tubes as well, that motor mount tubes and body tubes and whatever just come in usually standard sizes of like 12 inches, 24, 36, 48, 60, so on by a foot. So you'll just have to cut off some at the end, or you could just buy a standard size and leave it as is if that works for you. That's why I chose to do 48 inches for the body tube, just so that I didn't have to make any extra cuts in it. You want to avoid doing as many cuts as possible, because that just introduces errors and things like that that can go wrong. So avoid cutting if you absolutely have to. Then the next really important thing, I also chose this to be blue tube, is one other thing before we move on. There it is, blue tube. The next really important thing, and I see this a lot in designs I review, people, they finish their design, but then when they go over here to the motors and configuration, which we'll go over to later, they can't add a motor. And the reason is because they did not go over to this tab right here that says motor and check this box. So what this does is it means that this inner tube specifically is allowed to house a motor. You can also have other inner tubes that do other things, like act as couplers or E-bays or things like that, which we'll see on a level 2 or level 3 design. But this, checking this box right here, means that you are allowed to now add a motor. If you do not check this box, you will not be able to run any sort of simulation on the rocket. The motor overhang here, generally speaking, the motors are not going to be flush with the bottom of the rocket. They might hang out by like a 1/4 inch, but I'm going to leave that as 0 for now until we actually add a motor so you can kind of see what's going on. Ignition, leave that as it is. Unless you have a multi-stage rocket, just leave this as automatic at launch with 0 seconds. Otherwise, you're going to really mess things up. Some of the other tabs that you also see here is cluster and radial position. And basically what this means is that you can have all of these green circles represent a motor. So you can have multiple motors basically set up in here, or you can have multiple motor mount tubes, and the radial position can change the position of those tubes with respect to the radius. So like polar coordinates, you have a radial distance and a radial direction in degrees, so that's polar coordinates right there. We're not going to mess with that right now because our design is just a simple design with one singular motor. Now the mass I found for this piece was, let me see, 4.13 ounces. Okay, and that looks good. So we're going to close out of there. And now you can see, if I zoom in, and you can zoom in by clicking on this right here, and then you can scroll over. Zoom in a little bit more. So now you can see how the fin tabs, it's hard to tell, but the blue line that's at the bottom of the tab matches up perfectly with the outer diameter, this outside red line of the motor mount tube. So the way that you can calculate that is, you know that there's a thickness of your body tube that the fin has to go through, and then it has to come down to the outside radius of your motor mount tube. So it's just a pretty simple calculation that you should be able to do. And for those of you doing it with me, I will of course, check to make sure that you've done it right before you cut. So don't worry too much about that. I will make sure that it's correct. So the next thing that you want to add is you want to go back to body tube again, and you're going to want to add your centering rings. What centering rings do is they keep the motor mount tube in place. The fins also partially do that, but the centering rings, you still will need them. So I'm going to click on centering ring right here, and you can see it adds this thick red line at the bottom of the tube here. The program is smart enough that it automatically calculates an outer diameter for the ring that will fit perfectly into the body tube. So remember, the inner diameter of our body tube was 3 inches, so the outer diameter of the centering ring, because it has to fit into the body tube, is going to be 3 inches. So it may actually be slightly smaller than that because, again, this isn't like a press fit thing usually, hopefully. You may have to sand it down too when you actually buy it so that they fit in. But for right now, for our purposes, you can leave that as 3 inches. And this diameter, the inner diameter of the centering ring basically looks like a donut, is 1.635 inches, which is the outer diameter of the body tube, or I'm sorry, the inner tube right here. That's automatically calculated when you check this box automatic. So the thickness, I found my centering rings were, let's see, 0.125 inches thick. And I used fiberglass. If you're going to use something like plywood, you might want to do a 1/4 inch thickness. But since I'm doing fiberglass, I feel safe enough to just go with an 1/8 inch. And then right here, what you want is, you see the centering ring is right here. What you actually want is, you want that centering ring to be basically sandwiched up to the side of the fin tab, and then you're later on going to add another one right on the top. So you have your fin tabs sandwiched between 2 centering rings, and it also connects to the motor mount tube, and everything just connects to everything else, so it's very secure. So for me, that means I have to put right in here for the position, negative 0.25 inches. So now if you looked really closely, you saw that that actually shifted up. So now it's perfectly lined up with the back end of the fin tab. And also another thing to note is, if I zoom in right here, you can see that there will be a little gap right here this actually runs all the way around the motor tube. This is like, I think, roughly 1/4 inch little gap. That is okay, but you don't really want a huge pocket in here. You don't want your centering ring, your first centering ring, to be like a couple inches deep into the tube, because then you can get some weird sort of like eddy currents, little whirlpools that come off of the back of the body tube, and they can go up into here and they can cause really bad drag problems. So you generally want this whole face to be relatively close to flush, just as flat as you can make it. The reason you also don't want your fin tabs to go all the way up to the back is you need some material right here to be holding those fin tabs in place. So I think this design is a good happy medium. And then the override for the mass, I measured out my centering rings on a scale. Let's see, I found them to be 0.548 ounces. Okay. I think that's good. And then you're going to want to add another centering ring. Again, it's auto-generated at the back. You're going to want to increase the thickness to 0.125 or whatever you need. And I'm going to make this -6 inches now. And you see that now this fin tab is perfectly sandwiched between 2 centering rings, the body tube, and the motor mount tube. So it's very secure in there right now. Make sure that every time you add another centering ring, you change the material so that they all are consistent. And of course the thickness and the mass as well. So again, that's 0.548. Okay, and now I'm going to do this 2 more times because this is a large, a very long motor tube, and if you don't put a couple centering rings like up here at the top, you can get some weird sort of like moments going on of forces going in angles that you don't really want. So I'm going to add another one. And you want your centering rings also, if possible, to be at least somewhat evenly spaced, just to kind of distribute the load. And I'm going to put that to -12 inches because I put the last one at -6. Fiberglass again, and 0.548. Okay, and one more. Again, you have to click on body tube every time that you do this. One more. 0.125 again, fiberglass, and I believe 18 inches. There we go. 0.548. Okay. Okay, so now you have your centering rings in place. Now this rocket could actually basically fly in its current state. You could put a motor in here and it would actually work. The only issue is you're not going to be able to recover it. You don't have any sort of parachutes or recovery equipment. It's just going to plummet to the ground and probably smash into a million pieces. So the next thing you're going to have to add is you need parachutes, but first you're going to need something for the parachutes to attach to. So you're going to have to put something in the rocket that the parachutes can attach to, but will also allow the ejection charge from the motor to push the parachutes and the nose cone out. So what some people do for that is, if you have enough space on the side here, some people drill a hole in one of these centering rings and they attach an eye bolt to it, and then they have a cord going up to their parachutes, and that cord then continues onto the nose cone. So there's like a string of the nose cone to the parachutes back to the body tube, and the whole thing is being held together, and there's an eye bolt right here that holds on the cord. But there's not a whole lot of room here, so I'm going to do something else. What I'm going to do is I'm going to add 2 bulk plates and then an eye bolt through them, and the bulk plates will have holes in them that will allow the force from the ejection charge from the motor to blast off the parachutes and the nose cone. So I select body tube up here, and then I click on bulk plate. And again, that gets added to the bottom. Again, the outer diameter is already going to be automatically measured to be the inner diameter of the body tube, but the bulk plate is very similar to the centering rings, except it's one solid piece. It's not like a donut shaped thing. The thickness for mine were actually 0.25, and I decided to make these out of plywood. So I go and select plywood right there, and then I'm going to move this up, and you can also, instead of inputting things, you can also use these little arrows. So I'm going to put it right about there. And let me check. Yep, yeah, 25 inches, there we go. And again, measured from the bottom of the pairing component. You can always change it if you want to. And so I'm just going to leave that there and generate another one. 0.25. And I'm going to make this one go just an inch or 2 on top of the other one. So probably about 1 inch. I'll make it 1.5 inches to 6.5. There we go. And again, always make sure you have the right material set, plywood. Now what you're going to want to add, and these parts are really just to account for mass, and also just so that you have like a list of materials, of things that you need. They're not really going to affect the simulation. These parts right here, the bulk plates and the eye bolt that I'm about to add. So, but it's still important to add them. Otherwise, the people who are doing your certification are going to say that you look like you don't know what you're doing. So definitely still want to have these parts in here, even though they don't technically matter for simulation purposes. So I'm going to go over here, and this is a new button I want to show you guys. It's really important and really useful, the mass component. So this allows you to just add a mass somewhere, and it has no structural or aerodynamic properties. All it has is a weight property and a density, basically. So it comes up as this black dotted line when you click on it. And I am going to put that mass, and again, this mass is accounting for the large eye bolt that I'm going to use. So I'm going to put it right down there, and you can change what type it is. This is just really for your own records. So I'm going to put it as recovery hardware, because that's what it is. It's, it's hardware that will, keep your parachutes intact and stuff. So I think a good approximation for this is roughly half of a pound. So that's about 8 ounces, because this is a pretty heavy duty eye bolt that I've purchased with some large nuts. You need 4 of them, 2 for each bulk plate. And the density, that's going to be calculated automatically. What you want to do probably is play a bit with the length here. So make it a little longer, because again, eye bolts, long and thin. And then make this, it's probably, I think, a 1/4 inch eye bolt. So something like that. And that's going to approximate it good enough for our purposes. Basically, how this works is that the parachutes are going to be attached right here via a shock cord. This eye bolt is going to be attached to these 2 plates, and the plates are going to be epoxied in place to the side walls of the body tube in a very similar way as to how the centering rings are put in place. But the bulk plates will have holes in them, and those holes will allow the transfer of the hot expanding gases from the ejection charge to move through the body and pop off the nose cone and the parachutes, while still holding the parachute in place, because again, this doesn't move. It just allows the gases to move through it. It also helps to deflect some of the flames and things that could burn your parachute. And it's a good holder for the dog barf insulation, or some sort of flame retardant cloth or things like that you could put on top to, again, further stop or diminish the chances of one of your parachutes catching on fire from an ejection charge. So I'm going to leave that as it is. Oh, and also mass components can also be changed in their radial position. So I could do something like that. Now it's 1 inch away from the center. Or if it's something like on the outside, mounted to the outside like a camera or something, I could, put it like that. But I'm going to leave it as 0 for right now. And now the next thing you want to add is your parachutes, and also a shock cord. So the first parachute I'm going to add is going to be the drogue. So the drogue parachute is a small parachute that, generally speaking, comes out at apogee. So I'm going to name it drogue because I'm going to have 2 parachutes that will have different properties, DROUGE, that will have 2 different properties. So I want to be able to keep track of what is what. The parachute I selected for this was 18 inches in diameter, and the line length is probably going to be about 12 inches, maybe more, probably more like 24 inches. Ripstop nylon is totally fine for the parachute, generally speaking. If you see that it says some other material on this list from whatever supplier you're buying it from, then you can change it to that. It's not going to be elastic cord. This would be like a rubber band, basically. It's probably going to be something more like the tubular nylon, but this is a very thick cord right here. It's 11 millimeters. This is going to be something more like for your shock cord. So I would probably go with the braided nylon. That doesn't really have too huge of an effect on anything. Anyway, so now you see you have a parachute generated right up here, and it's in position relative to the top of the parent component. So I want to move it down a little bit into the body tube right there. That looks good. And then it's not, you can change the length, like the size. So if you know how much volume your parachute is going to take up, sometimes if you have a rocket that has a lot of, components inside of it, like electronic components. If you're doing like a level 3 rocket, it may be important to measure how much volume your parachute is going to take up. But in this case, it doesn't matter too much because we're dealing with some generally pretty small parachutes. So I'm just going to increase the packed length to about 4 inches and the diameter to about 2 inches right there. That's probably pretty accurate. Then this is really important right here. So deploys at. This means that you can select when you want your parachute to deploy, whether it's going to be at apogee or the first ejection charge of the stage or at a specific altitude or something else. So I am going to select apogee for this case because that's generally speaking true. Apogee is the highest point that your rocket is going to reach, so that's right at the peak altitude that the rocket will reach just before it starts to fall down. That's generally when your ejection charge is going to go off. For this type of rocket, for a level 1, you will have to set the ejection charge manually, and we'll talk about that more when we're adding a motor. For right now, I'm going to select apogee, and 0 seconds, you can leave that just as it is. So I'm going to close out of there, and now I'm going to add another parachute right here. This is going to be our main. So this one is going to be, generally speaking, below the drogue parachute. I'm going to change that to main. And then I'm going to make the diameter of this to 48 inches. So this might be a little bit overkill for this rocket. But it should probably still be okay. If you want to go with a slightly smaller parachute than 48 inches, you probably will be fine with that too. And the line length is about 36 inches for this parachute. So, and I'm going to increase the size. This one's going to be bigger than the drogue, so probably something like that. Now, this one, you're going to want to change this from deploys at. Again, this is for the main parachute. This is going to deploy at a specific altitude during descent. So how this works is that both of the parachutes get shot out, but only the drogue actually unravels. The main is still held together in like a ball, basically, and is just kind of dragging along there, but not actually inducing very much drag force because it hasn't deployed, it hasn't unraveled. And how that is done is usually using a Jolly Logic. That's a little device that you can wrap around your parachute that will unlatch. It's like a miniature altimeter that you can set to unlatch from the parachute at a given altitude. So when you set specific altitude during descent, this dialog will come up here. So the altitude, I'm going to set that to be, I don't know, about 700 feet. Generally speaking, you don't want to set that to be less than 500 feet for a level 1 rocket. But the people at the launch site, when you're actually going to launch this, will tell you what they recommend for your altitudes to set your Jolly Logic to. It will depend on the size of the launch site and the wind conditions of that day and the weight of your rocket really are the main 3 things. So I'm going to leave that. All things look good on here. Oh, and also the elastic cord you might want to set to braided nylon. There we go. And now you want to add a shock cord. So that's right here, shock cord. And I'm going to put that right about here because it's going to be wrapped around really both of these parachutes. I actually probably want to put it more so at the bottom because it's going to be connected to this. And that is basically, it's just basically a long rope that's going to hold everything together. So your drogue parachute, your main parachute, your Jolly Logic, your nose cone, your body tube, it'll all be held together by the shock cord during descent. So I'm going to go with tubular nylon, 11 millimeters. That's like roughly a 1 centimeter rope. So, and then the length is going to be a lot more than 15 inches. You probably want it to be at least like 60 inches for a rocket of this size, maybe even larger. I'm going to go with 60 for right now. So that's probably good right there. So now you have all of your components except for your Jolly Logic, which I'm going to add as a simple mass component. And I'm going to call this Jolly Jolly Logic. And I'm going to put that around the parachute right here. And I'm going to make that be, it's kind of like an altimeter. So I'm going to set it to be an altimeter. And the mass I found was 0.635 ounces. Doesn't have too huge of an effect, but it's still a nice thing to have on there. Okay, so that is all for the actual design of the rocket itself. The next steps are going to be to add a motor. So right now you see you have a stability of 2.88 and some other things, but you have no apogee measured. Your mass is measured with no motors. All of these stats, your mass, your stability, your apogee and stuff like that, they are all going to change really drastically when you add a motor. So that is the next step. This video has already gone about 45 minutes, so I think I'm going to end it right here. If you are interested, please continue with watching the next video, which will be how to add a motor to the rocket, as well as do some simulation on the rocket to make sure that you're getting the kind of flight performance that you want. Thank you, and that's all.